Welcome to this video lecture on the central limit theorem that corresponds to, roughly speaking, the second half of chapter 4 in the Stat 314 textbook. The lecture is going to consist of 4 of these sheets of paper, the first of which you see before me. I would suggest that you might consider pausing the video and copying down this first sheet and then playing the video and walking through it with me as I go through it. So I'll give you about 3 seconds to pause here if you wish, and then I'll continue on. All right, so in chapter 4, we're concerned with figuring out the center and spread of a sample distribution. So perhaps we've got a sample distribution of a mean of, the test statistic is a mean of some samples from a population, and we'd like to know what's the middle of the sampling distribution and what's its spread. So what's the mean and the variance, or the mean and the standard error of this sampling distribution. And as we mentioned earlier, there are 3 ways we can do it. We can approximate it using a bunch of simulations. We might be able to calculate it exactly if we can use some special formulas, for example, with maxes and mins of known distributions, or perhaps the number of permutations of the data set is small enough that we can compute all such permutations and then take the mean and standard error of the sampling distribution that results. Or we seek to approximate these values. And one of the big ways via simulation or via the central limit theorem, which we'll take the rest of this lecture to sort of speak through. So we're going to use this theorem or formula to approximate the mean of a sampling distribution. And the idea is, which the lecture from Professor Knudsen illustrated, is that if we take a large enough sample, our sample mean starts to behave like an approximately normal distribution. So if we take 8,000 samples, like the mean of 8,000 different samples, and plot its histogram, that histogram is going to start to look normal. And if it doesn't look normal with 8,000 different permutations, then maybe with 80,000 it does, okay? Right. Well, so here's the central limit theorem. And it's kind of magical. So let's kind of talk through it. Central limit theorem says that if I have x1 up through xn independent and identically distributed IID random variables, which means they'll all share the same mean, which will denote mu, and the same variance, which will denote sigma squared. Both of these need to be finite, by the way. Then x bar, the mean of x1 through xn, is approximately normally distributed with mean mu and variance sigma squared over n. And this approximation gets better as n approaches infinity. So as n approaches infinity, I can kind of standardize that x bar by subtracting its mean and dividing by its standard deviation or standard error. And if that's less than or equal to z, I can approximate it using the standard normal CDF on z. And as n goes to infinity, that approximation becomes exact. And that's kind of magical, which is why I'm using my son's Harry Potter wizard wand to display it. Okay, so that's the central limit theorem. You've seen it in Math 313, and we'll see it a fair bit more in this class. So first off, this mean mu and this variance sigma squared over n, these are not a surprise. So in class, we learned that if each xi has mean mu, then the expected value of the mean of all the xi's is still mu, and the variance of the mean of all those xi's is given by sigma squared over n, okay? So that's true anytime we have independent and identically distributed random variables. So we shouldn't be surprised by that mean or that variance. The wonderful news is that x bar is approximately normal. That's the wonderful news. Okay, now in practice, if we don't know what distribution our data is coming from, we don't have the mean, the mu, or the sigma squared. So oftentimes we'll use the expected value of x bar that we get from a bunch of simulations and the standard error of x bar, which we get from the simulations as well if we run a bunch of permutations on the data, we can generate an approximation. Well, we can generate the expected value of X bar and standard error of X bar via R. And in this case, we say that this quotient is approximately standard normal, okay? And keep in mind, this is just standardizing X bar in some sense, subtracting the mean, dividing by the standard deviation or the standard error, okay? All right, well, all this is supposed to work as n gets large, as n goes to infinity. So what do we mean by large n? Well, traditionally, 20 years ago, before the advent of powerful and portable computing power, we would say that you should probably have at least 30 x sub i's, all right, to take the mean of, and then it starts to behave normally. It's not a great rule of thumb because, as Professor Knudsen mentioned, that depends kind of on the spread and the mean of the distribution you're dealing with. However, this second one is still a decent rule of thumb. If your xi's happen to be from the binomial distribution with n trials and probability of success p on each trial, then large means that n times p should be greater than or equal to 10, and n times 1 minus p should be greater than or equal to 10. So as long as those two things hold, you're safe to use the central limit theorem. And again, these rules start to become less important as we use more and more bigger computer, stronger and faster computers so that we can use more permutations. And when we get to bootstrapping, we can bootstrap more data sets to do this with. All right, so on this page, I'm going to go through an example or two and also switch over to some R code. So I'll let you have a minute or two to copy this down, pause the video, and then start it again when you're ready. I'll give you a 3-second count before I start chunnering. Okay, so this is example 4.7 in our text. We are told that x1 up through x30 are independent and identically distributed from a gamma distribution with r equals 5 and lambda equals 2. As the example mentions, you might recall that a gamma distribution is simply a sum of Poissons, all with the same lambda value. So in this case, a gamma distribution is a sum of 5 Poissons, each with lambda 2. So if Poisson is modeling the amount of time between occurrences of some events, like a customer entering a store, then if I say r equals 5, I'm looking for how long should I expect it to be before the 5th customer enters the store from the start of the day, with lambda equals 2, so the average wait time being 1/2, I don't know, hours or minutes, depending on the units, okay? All right, so we've got this gamma distribution, and we're looking to approximate the probability that x bar is greater than 3. Cool. So, little facts about the gamma distribution that you might have forgotten, which is understandable, and I do not need you to remember all the variances and means of the various distributions. The expected value of a gamma distribution is the r divided by the lambda. So in our case, that would be 5/2. The standard deviation is the square root of the variance, and the variance is r over the lambda squared. So in our case, we have a standard deviation of approximately 1.118. That's a calculator approximation, okay? All right, so let's attempt to calculate the probability that x bar is greater than 3. Now I've got n equals 30, so let's just say we feel safe with the central limit theorem. So I'm going to first subtract the mean from both sides and then divide by the standard deviation over the square root of n, which is exactly what the central limit theorem from the previous page told us to do, all right? Because the standard deviation of xi divided by the square root of n was the standard deviation of x bar approximately according to the central limit theorem. So I subtract the mean, divide by the standard deviation of x bar, and I do that on both sides. And the central limit theorem says, well, hey, guess what? Now on the left, that's the standard normal, approximately the standard normal variable. And the right-hand side calculators out to 2.4495. So I bust out my standard normal CDF. And since it's z greater than 2.4495, I do 1 minus the CDF of 2.4495. And the tables tell me that the CDF of the standard normal at 2.4495 is approximately 0.99286. So I get a probability of approximately 0.00714. Now, I can also try and simulate this on R. So I'm going to switch the screen view to my RStudio shell. And this is from the chapter 4 code available on the on our Canvas website. And so here's the code for example 4.7, which is what we're working. If you set seed to exactly what I've got, I believe that means we're going to generate the same random sample. You can tell me if I'm wrong or if you wish. So I'm going to run that. We're going to run 10 to the 5th trials. I create my output vector with n entries. And then for 1 through n, I'm going to generate 30. I'm going to generate R gamma with 30 entries. Yeah, I'm going to generate 30 random variables from R gamma with a shape of 5. So that's 5 Poissons added and a rate, a lambda value of 2. And then I'm going to record the mean of those 30 randomly generated variables. I'll show a histogram, do the QQ plot, etc. So let's run through it. I'm going to run the loop now. Doesn't take too long. Throw you the histogram there. And you see that that thing does look like a normal distribution, okay? Peaking around 2.5. And if I check the X bar values, for some reason this plot takes a few seconds to generate, I get something that looks pretty darn linear. And if I run the line through it, you don't even see it because of the density of the data points it's trying to plot. All right. Well, the mean of X bar is 2.499, in case you're interested. We calculated it to be 2.5. The standard deviation is 0.20314. And we didn't actually calculate that because we didn't quite divide by 30. And then if I take the sum of X bar greater than 3 and divide it by n, that'll tell me the probability of it. And I'm getting 0.00927. So slightly different value than what we got from the central limit theorem approximation. But I'm taking the, and then another way of doing that same command is just mean of X bar greater than 3, and I get the same value, okay? So the approximation via R is somewhat different than the approximation via the central limit theorem. Strangely enough, the textbook, when it does this exact code, it seems to be getting a value in R far, far closer to basically 0.007. And I'm not quite sure why that is. Okay, but this is how we could approximate the value of X bar, or the probability of X bar is greater than 3 using R code. Oops, I'm going to stop sharing now. Okay. All right. Well, next thing is, we oftentimes apply the central limit theorem to binomial data, and nothing about the central limit theorem changes with binomial data. But because we do it a lot, we might as well run some examples with it and give you more of a custom fit corollary for the binomial. Okay, well, one thing to recall is that if I give you a random variable from a binomial 300p distribution, that means the random variable is telling me how many successes there are in 300 independent Bernoulli trials where the probability of success in each one is p. In other words, I'm taking 300 Bernoulli trials. Remember, Bernoulli trial is one trial, probability of success p, failure 1 minus p. So I'm taking 300 Bernoulli trials and adding up the number of successes, okay? All right, so here's the problem. We're going to toss a fair coin 300 times, and I'd like to approximate the probability of getting at most 160 heads. Now, technically, we can do this problem and get the exact answer. This is binomial 300, 0.5, and I could calculate the probability of getting x equals 0 successes, x equals 1 successes, x equals 2, all the way up through x equals 160 successes. And I have the PMF of a binomial, right? What is it? Probability that f of x is equal to n choose x, p successes, x successes, and n minus x failures, right? So I could do that for x equals 0 through 160 and add them all together, and that would obviously take a long time. So we might prefer to approximate it. All right, so I recognize that each trial is Bernoulli with 0.5, and I have 300 trials. You might recall that the expected value of a Bernoulli trial is the value of p, and the variance of a Bernoulli trial is the p squared, which in our case would be 0.25. So we are asked to compute the probability that the sum of these xi's is less than or equal to 160. But the central limit theorem is talking about a mean. So to get into the CLT zone, I'm going to divide that sum by 300, because that tells me the mean value of xi. In other words, it's telling me the proportion of successes. All right, well, whatever I do to one side, I do to the other. So I divide both sides by 300. And that means I'm now asking the question, what's the probability that x bar is less than or equal to 160 over 300? Okay, and x bar being the proportion of heads. Now, from the central limit theorem, we know that x bar is approximately normal with the same mean as each of the xi's, and the variance of the xi divided by the number of trials. So that's my new variance. So the problem then, the solution to the problem. Probability that the sum of the number of successes is less than or equal to 160 is the same as the probability that the proportion of successes is less than or equal to 160 over 300. Proportion of successes is just x bar. I'm going to subtract x bar's mean and divide by x bar's standard deviation on both sides. The central limit theorem says that this quantity on the left is simply my z, and I computed via calculator the quantity on the right to be about 1.155. Give it to the central limit theorem, standard normals CDF, and I get a value of 0.8759. Okay, so that was the central limit theorem applied to binomial data. Okay, going to do basically another identical example, but if you wish, you might find it useful to memorize this corollary to the central limit theorem. And a corollary basically means this result is saying very much the same thing the central limit theorem did. In this case, the corollary is simply applying the central limit theorem to a binomial distribution. Okay, so I've got a binomial distribution, n trials, probability of success in each trial is p. P hat is going to be the proportion of successes. So the number of successes x divided by the number of trials n. All right, and again, assuming np and n1 minus p are large enough, greater than or equal to 10, then the sampling distribution of p hat is normal, right? With a mean that's the same as the mean of p hat, which is p, and the variance is the same as the variance of x over n, and that would be p times 1 minus p over n. And these are exactly what the central limit theorem said. Similarly, if I didn't want to know about x over n, if I wanted to know about x, the number of successes, the sampling distribution of x is also approximately normal. And now the mean of x, you can calculate that. We know from Math 313, the mean of a binomial is n times p, and the variance of a binomial is np1 minus p. So we knew the mean, the variance from 313, and the central limit theorem is just telling us x is approximately normal with that mean and variance. Okay, well, let's take that thing for a spin. I'd like to approximate, or I've got x binomial, 120 trials. Probability of success in each trial is 0.3. And I'd like to approximate the probability that x is less than or equal to 25. Okay, well, just some review. Expected value, n times p. Variance of x, n p 1 minus p. Or if you prefer the expected value of the proportion of successes, I can drag the 120 out, throw in the expected value of x from over here, and simplify. And the variance, well, the 120 comes out squared. The variance was 25.2 from prior. And that gives me a standard deviation of 0.04183 or a variance of 0.04183 squared. Okay. And if I just check, I notice that my n times p and my n times 1 minus p are both well greater than 10. Okay. All right, well, by the above corollary, this x bar, this p hat, this x over n, is approximately normal with a mean of p and a variance of p 1 minus p over n. In other words, x bar is approximately normally distributed with mean of 0.3 and a standard deviation of 0.04183. So I'm looking for the probability that x is less than or equal to 25. I can divide everybody by 120 to get my proportion, my mean x bar. I can standardize my x bar using its mean and standard deviation of 0.04183. And the central limit theorem tells me that the standardized variable on the left is actually pretty much the standard normal. And then via the tables, I can get that value is about 0.014. Okay. Now, given the wonderful world of powerful computers we live in, I can also calculate the probability that I have x equals 0 successes, x equals 1 success, x equals 2 success, all the way through x equals 25 successes, since x is simply binomial, and I can get an exact answer of about 0.0159. So those two answers are somewhat close, okay? All right, but again, this is simply the central limit theorem. You don't need to ever memorize this if you don't want to. We are simply using the central limit theorem with the mean being the mean of x and the variance being the variance of x divided by the number of trials. All right, so this is the last page, and it presents a bit of a wrinkle or slight complicating factor with the central limit theorem when we attempt to use it on discrete random variables. So I'll give you a few seconds to copy this down and then I'll go through. All right, so hopefully you paused it and took the notes down. So in the previous two binomial examples, in both cases, I didn't work with x, the number of successes, which is a discrete random variable. I could have 1 success or 0 or 3 successes, but never 1.8 successes. I instead work with the proportion of success, and that can take on any real number within reason between 0 and 1, since it's x, the number of successes, divided by n, the number of trials. So the proportion of successes is a continuous random variable, and the normal distribution is also continuous. We run into slight problems when we attempt to use the CLT to approximate a discrete random variable. And I believe you've seen this in 313, but it's worth revisiting here, all right? So when we have a discrete random variable and we attempt to smack it with a central limit theorem, I have to make sure I make an appropriate continuity correction. And this image down here will make a bit more sense when I get to it. All right, so here's an example. We have an unfair coin that we're going to toss 8 times, and we're going to record the number of heads we get. And we're going to assume the coin is unfair. So in this case, the probability of heads is 0.4 instead of the normal 0.5. And I would like to approximate the probability that I get a 3 or a 4. So perhaps I'm trying to make some gambling game with this cheater coin, and I want to figure out what my payoff should be if somebody flips 3 or 4 heads out of 8. Okay. All right. Well, X is clearly binomial distribution. There are 8 independent trials and identical. Each has a probability of success, heads, of 0.4. Now, by the central limit theorem, that corollary from the previous page, X, the number of successes, is approximately normal with the mean 8 times 0.4 and variance 8 times 0.4 times 1.4, which I simplify to 3.2 and 1.39 squared. And yes, I know that 8 times 0.4 and 8 times 1 minus 0.4, neither of them are greater than or equal to 10. This is just an illustrative example, okay? All right. Well, so if I'm trying to calculate the probability that X is 3 or 4, that means I'm trying to calculate the probability that X is between Well, 3 is less than or equal to x is less than or equal to 4. Okay, and this is where the issue comes in. So down here, you should imagine these dots as the probability of 1 success in 8 trials, whatever that height is the probability. Probability of 2 successes is the height of this dot. Probability of 3 successes is the height of that dot. And in the discrete world, I simply add these probabilities, these heights. But I'm about to flip over into the continuous world by trying to move to a normal distribution, which is going to calculate probability by adding up areas or integrating areas. So I need to move away from these discrete dots to something that has area in it. So a naive idea to do that is to simply take each of these heights and make them 1 unit wide bars. So now this first bar has a width of 1 and a height of whatever the probability of 1 was. So the area of this bar is the same as its height, but now it's an area that's telling me the probability instead of just the height. And so on. I make each height into a bar of width 1, and I've got what looks like a histogram. And if you like, before I go on, if I want the probability that x is 3 or 4, it looks like I'm looking for the area from 2.5 to 4.5 to add up the areas of those 2 bars to get the probabilities, right? So I've translated from discrete heights to areas. And if you like, you could imagine a normal distribution connecting those dots. And I'm going to standardize and find that area using tables. So I translate from 3 less than or equal to x less than or equal to 4 to 2.5 less than x less than 4.5. And you know what? It doesn't matter if you do less than or equal to, since we're now continuous, and area doesn't care if you include 2.5 or don't. It's the same area. Okay. Now, recalling that x is approximately normal 3.2, 1.39 squared, subtract my mean. I divide by my standard deviation or standard area in all 3 spots. And the central limit theorem tells me that that variable in the middle is approximately standard normal. And then I do my standard normal CDF values. The value of minus 0.5 is 1 minus the CDF at 0.5. And then for my table, I compute those numbers and crank out an answer. And so that step, going from 3 to 4 to 2.5 to 4.5, is called the continuity correction. Similarly, if the probability was looking for if the question was looking for the probability that 3 is less than or equal to x is less than 6, I need to again start at 2.5, but I don't want to include 6, so I don't want to include any of 6's bars, so it looks like I would stop at 5.5. The bar should always be 1 unit wide. So I go from 2.5 to 5.5, and now I could continue with my standardizing, invoking the central limit theorem to say that's approximately normal, and away we go. Okay, so I hope you find this helpful. Remember, the R code is located in the files folder on Canvas, and I believe you have everything you need now to take a good crack at the homework problems from chapter 4, which are also posted on Canvas.